Welcome. In this video, we're going to discuss some basic linear programming. And linear programming involves maximizing or minimizing a situation that has many constraints or restrictions. And a simple way for me to help you think about this would be to think about something which is kind of akin to what we call the traveling salesman problem, but think about your UPS or your postal driver. They start their day at the depot. So now let's imagine there were no rules and our UPS driver, he just grabbed all of his packages and he said, well, I'm going to drive over here to Wrightsville Beach and now to Carolina Beach and now back to downtown, now to Midtown, over here to Leland, back to Wrightsville Beach, over here, back down there. Is that what he's going to do? No, because that doesn't make sense. He's going to pick up his packages and he's going to make his first stop, and his second stop's probably right beside that, and his third stop is right there, his fourth stop, etc. He's going to make it in some order where he eventually turns around and comes back to the warehouse, right? So the least amount of stops, the least amount of turns, all in the same order so that it flows nicely and the packages are organized to be delivered in a specific manner. So that's kind of the idea of what we're doing here, but we're going to do it with a silly biscuit problem. So we're dealing with Golden Harvest Foods, and they make both jumbo and regular biscuits, two types of biscuits. We have quite a few constraints that we have to deal with. One is that we can only cook 200 biscuits per day. Another constraint is that the jumbo biscuits require 2 ounces of flour, but regular biscuits only require 1 ounce of flour. Also keeping in mind, we have a finite quantity of flour. We only have 300 ounces of flour available. And then we make a different amount of money. So we make 80 cents if we sell a jumbo biscuit versus our income for a regular biscuit sale would be 50 cents. What we want to determine is how many of each size biscuit, how many jumbo and how many regular biscuits should we make in order to maximize our income? And what is the maximum income? So what we're going to do here is we're going to use these constraints to graph all of these linear inequalities and determine what our optimal solution set might be. So let's focus on setting our constraints up first. And in order to do that, we need to identify what our variables will be. I'm going to let X represent regular biscuits and Y will represent jumbo biscuits. If we know the oven can cook at most 200 biscuits per day, well, that means that X plus Y, the sum of all my biscuits, jumbo and regular, must be less than or equal to 200. Right? We also know our quantity of flour. We only have 300 ounces total, 2 for each jumbo and 1 for each regular. So I'll say 1x plus 2y, and that needs to be less than or equal to 300. And oftentimes with real life problems, we have constraints that we need to include. So the idea here is, can you make negative biscuits? And the answer is no. So that means that X, my regular quantity of biscuits, needs to be greater than or equal to 0. And that's the same with Y, my jumbo quantity of biscuits. That also needs to be greater than or equal to 0. All right, so let's look at graphing our constraints, the situations that restrict the quantity of biscuits that we can make. Here I've pulled in my graph paper. And because I have already worked this problem out, I'm counting by 100s on my X and Y axis. So I've got a nice scale here. All right, so graphing X greater than or equal to 0 and Y greater than or equal to 0. Well, x equals 0 is a vertical line. Greater than would be to the right. And y equals 0 is a horizontal line. Greater than would be above. And so all these two constraints are doing, they are restricting us into quadrant 1. They're just saying, hey, we have to have a real life situation. So let's look at graphing my red and my blue lines. So here, this is the same as x plus y equals 200, or rather y equals negative x plus 200. And now that's a line with a y-intercept at 200 with a slope of negative 1. So we've got that line showing up right there. And obviously, if we were graphing it, we would continue in either direction, off to the left and right, but we're restricted again to quadrant 1. All right, let's look at the other equation, which is x plus 2y equals 300, which gives me 2y equals negative x plus 300, or y equals negative 1/2 x plus 150. So that means my y-intercept is at 150 right here, and we'll go down 1 over 2, which takes us to 300. So my lines look like this. I've got these vertical boundaries, which I removed, but I'll put back in, from x being greater than or equal to 0 and y being greater than or equal to 0. So now we already said that looking at shading these, that would keep us in quadrant 1. Let's look at shading x plus y less than or equal to 200. So if I picked a point down here, such as 0, 0, which is not on my blue line, is 0 plus 0 less than or equal to 200? And the answer is yes, so we would be shading below the blue line, but in quadrant 1. And then we have the same situation for x plus 2y being less than or equal to 300. Is 0, 0 plus 2 times 0 less than or equal to 300? And I would say yes, so we would be shading down here. And then, of course, the solution set is going to be the region where we have that double overlap. So what we find is that all of my overlapped regions together create this quadrilateral shape. So this represents my optimum area. And using more advanced mathematics, we can prove that the maximum and minimum values for optimizing this region will occur at the vertex, or these vertices, these corner points. Now, I'm not going to show you why, because you do not have the skills for that yet, but that is where the max and mins occur. So we need to know what all of those corner points, or those ordered pairs, are. Well, these three are pretty easy. We have the origin, 0, 0. We have a y-intercept, 0, 150. We have an x-intercept, 200, 0. And then we need to know what this point is right here, this point where the red and the blue lines are intersecting. And this blue and the red line came from these two equations, y equals negative x plus 200 and y equals negative 1/2 x plus 300. So that point of intersection would be solving that system of equations. And since they're both equal to y, I can let both the left and the right be equal to either of these two equations. So I'll say negative 1/2 x plus 300. Solving that, I will get that 100 equals x, which lets me know that this vertex point right here is 100 for x, and plugging 100 into either of these equations, you get 100 out for y. At this point, we have found our solution set region, and we know what our 4 possible solution vertices might be. So let's go back and think about what we're being asked to maximize. We want to find how many of each biscuit needs to be made in order to maximize our income, and what is the maximum income? Well, that's where this other information regarding the income comes into play. Our total income for our target equation, we're going to get 50 cents, or 0.5x, plus 0.8, 80 cents for each jumbo biscuit, y. So we want to determine what that maximum income will be. So as I've said, we have these 4 vertices here. So I've made a table, and I'm going to look at each of my 4 combinations. Let's see, we've got 0, 0, 0, 150, 200, 0, or 100, 100. So those are the 4 options for X regular and Y jumbo biscuits that we can make that could give us maximum income. So I'm going to plug each of these ordered pairs into my income function. So I equals 0.5 times 0 plus 0.8 times 0. If we make 0 jumbo and 0 regular biscuits, my income will be $0. I will have nothing to sell. So we knew that wasn't going to be the answer. All right, let's look at making 0 regular and 150 jumbo biscuits. That ends up giving us $120. All right, our next one, we'll look at making only 200 regular biscuits and 0 jumbo biscuits. That makes us only $100. And then lastly, if we make 100 of each, 100 regular and 100 jumbo, we end up with an income of $130. So that is my largest income value, and that lets me know that my maximum income is $130 when 100 regular, X was regular, and 100 jumbo biscuits are made. So the way we might write our solution, the maximum income is $130, and that again is when 100 regular, because X represented regular, and 100 jumbo biscuits were made. And normally somebody says, well, Miss Stein, you had 300 ounces of flour. Why wouldn't you have just made 300 regular biscuits, since regular biscuits only require 1 ounce of flour? But you have to keep in mind, we have that other constraint. You can only bake 200 biscuits per day. So even though we have leftover flour at 200 regular biscuits, we can't bake more because the oven only permits 200. And over here, we can't bake 200 jumbo because we only have 300 ounces of flour, and each jumbo biscuit requires 2 ounces of flour. So that gives us, the flour limits us to only 150 jumbo biscuits. So again, this was just kind of a really simple problem for us to see or understand how to find a maximum situation where we have lots of constraints, lots of linear inequality constraints. So as always, please feel free to email me with any questions or concerns if you have help, if you want help, if you need help, because I would love to help you. All right, good luck out there.